All right. Hello, everyone. Good evening. Thank you very much for joining me for this session here about Cloud Spanner, Google Cloud Spanner. My name is Robert Kubis. I'm a developer advocate for the Google Cloud Platform. Probably most of you by now know what the Google Developer Advocates do, but just for the ones that don't know yet, we are understanding our job as a bidirectional interface between you who built on our platform and the developers inside of Google that built the platform. So please, please, please reach out to us if you have feedback, constructive feedback, if you think some things are just too complicated and could be much easier, if you have some really cool project on Google Cloud Platform that we can get promoted for you. So please, please reach out. To me personally, you can reach out on Twitter under the name Hossi. All right, what do I gonna talk about today? This is a tools and action session, so I'll try to concentrate mostly on code, but I still wanna first and foremost want to get everybody on the same page and also frame a little bit around like why we built Spanner inside Google. So I'm gonna go into a little bit of a history, go into some architecture, and then spend hopefully the majority of my time on some coding and demo of Cloud Spanner. All right, so to get the motivation why we built Spanner, we have to go back a couple of years, around 10, 12 years. And back then, Google was a massively growing business, and our ad system, which was our revenue driver, was backed on a sharded MySQL system. Now, this sharded MySQL system was sharded by a custom ID, and we had to reshard it several times. Now, the last reshard actually took us multiple years, and we definitely saw at that point that this wasn't a viable solution to go forward. We needed a system that could scale with our business. We were growing from like a 10 million to $1 billion company, and we needed something, a backbone that could support that. So what were the requirements for that database that we needed? First and foremost, we needed a database that could scale, and that could scale horizontally. There's just no way to scale something like that vertically. Second of all, we were dealing with budgets, monies, partners, agencies, customers. So we were dealing with something where eventual consistency was just not an option for us. So we needed something that supports ACID, transactions, and global consistency. And third, Google is a 24/7 business. We are dealing with money all around the world, and if Google ad system is down, not only Google loses, much more importantly and much worse, our customers losing money. Right? So we needed a system that could actually be maintained and evolved, and we could innovate on it without any downtime. So now we built this system inside, and we have it running for almost 10 years now inside the company, and many of our products are actually backed by Cloud Spanner, and more are coming that are backed by Cloud Spanner. Gmail is one of them, the Play Store, there are many others. The ad system as one of the first customers. Now, to make that available to all of you, we needed to package that into basically what we offer through our developer console and through our APIs under the Google Cloud Platform umbrella. So first, we wanted to have it fully managed in a way that you could go either use our APIs or the developer console and create an instance, and then create database, a schema, and load data. Second, we wanted to tap into the knowledge pool that is out there. Like, there are so many people out there that understand what relational database systems are, and they understand what SQL is, and they feel familiar with it, they feel comfortable with it, and we wanted to tap into that pool. So we didn't want to create a proprietary interface to Cloud Spanner. It was very, early on, very important design decision that we made. As mentioned, we needed ACID transaction, we needed global consistency. With global consistency, basically the requirement for an automatic and synchronous replication came in. So Cloud Spanner can be globally replicated. And we also needed to integrate with other features like IAM, like enterprise features, so identity and access management. We were focusing on building out client libraries, Java one of our prime client libraries, but also others like Python, Go, Node.js, and so on, and more are coming. Now, what is Cloud Spanner in terms of like the constructs that you have in Cloud Spanner? I want to bring everybody on the same page so you basically can follow easier along when I talk about these different concepts. So everything starts with an instance. An instance is basically your resource pool. You define like how many nodes you want to have, and that basically gives you a barrier of how much storage you can manage with that with these resources. Now, if you are under that limit, you can always scale in and out, but you have basically that limit, like per node, you can manage 2 terabytes of data. If you have more than 2 terabytes of data in your database, you cannot scale back to 1 node. You have to at least have 2 nodes. In your instance, you have databases. You can create up to 100 databases in your instance. And then you have tables. You can create up to 2048 tables in a database. Now, these are terms, database and tables, that everybody who is familiar with relational database system knows. Now, we needed a concept internally that enables us to actually scale, to horizontally scale. So internally, we have a concept of splits. And a split is nothing else than we basically take your table ordered by primary key lexicographically, and then we chop it up in parts. So you basically, if you have a table with 1,000 columns, with 1,000 rows, or 10,000 or a million, then we take we define chops or parts of that table, which we call splits. Let's say splits by 100 or splits by 1,000 rows. And that enables us to distribute the responsibility of these splits to different worker nodes, and by that enabling horizontal scalability. So how does that look like? So we have a separation of compute and storage. So if you buy or rent one of our Cloud Spanner instance nodes, you get actually 3 in a regional configuration, and we have multi-regional coming up later this year, and there we have even more replica nodes. But let's concentrate on the regional instance right here. So in this case, what you see here, you have a 3-node Spanner instance, and these 3 nodes are replicated in 3 zones of 1 region. Now, they are independent from storage, but each zone has basically dedicated storage for the compute resources. Now, why do we need this? Distribution of work is one reason, of course, but the other thing is also, I mentioned, no downtime. So we need actually a replication for making sure if any kind of worker node falls down, or we have a network issue or anything, that we have replicas of the data and still the database can operate. Now, there is one challenge with this. If you have multiple replicas, you need somehow keep them in sync. And usually the way that you do this is that you define somebody who is responsible for the entire group of replicas. And you need to make sure that there's, on one hand, only one leader of that group. And then we also wanted to remove things like massive communication. Now, communication is really expensive, especially in a distributed way. If you need to use a lot of communication to keep consistency, your database is basically slow. And in normal databases, if you look at traditional databases, you have 2 PC, so 2-phase commit protocols, or 3-phase commit protocols to keep consistency. We use the 2, but in a different context. Now, we could cut down a little bit on the communication by using something that we call TrueTime. So what is TrueTime? I want to step back a little bit to explain TrueTime. If you would now look to your neighbor and compare watches, and you would synchronize your watches, and then you go out and you come back after a week, or let's say a month, then it's very, very highly likely that your clocks have drifted. It's actually certain that your clocks have drifted. Now, it's a challenge, especially if you need something that you can trust globally. And we wanted to actually use a timestamp, a global timestamp, global wall clock time that we could trust. And if we can actually trust the global wall clock time, we can reduce the communication, because we can use this to ensure the serializability and the global consistency. Now, as mentioned, you cannot take a couple of watches, synchronize them, and then go out and basically distribute them in multiple data centers. You need something else to synchronize these watches. So what is TrueTime? So since we cannot really synchronize these watches to a timestamp precision, we needed something to quantify like an uncertainty, the drift uncertainty. So that's where TrueTime comes in. TrueTime is not a single timestamp. TrueTime is actually an interval. You get a lower and an upper bound. Now, the lower bound basically defines a timestamp, which by the time the TrueTime.now has finished, has definitely passed everywhere in the world. And the upper bound is the timestamp that definitely has not passed everywhere in the world. And now, like the difference of that, we call epsilon, which is basically this uncertainty. And using this interval, we can actually ensure that there's exactly only one leader for a group of splits, which we choose and use Paxos protocols to choose that leader. But we can make sure with TrueTime that there's exactly only one leader for a group of splits. And by that, we have the one guarantee to do the global consistency. Now, how do we get this drift down, like get this epsilon down, this uncertainty epsilon? It's really important to keep that as low as possible, because if it's large, your database is slow again. So we need to keep that as small as possible. And what we did is we equipped all our data centers with hardware. On one hand, atomic clocks, and on the other hand, GPS clocks. And now we use GPS to synchronize our atomic clocks across the data centers and keep the epsilon as small as possible. We keep it in a very low single-digit millisecond range. Now, so we synchronize them every 30 seconds, and then if we want to have a TrueTime timestamp, we basically go out and say, like, I want to have a TrueTime timestamp. We take a subset of our time masters, of our GPS time masters and atomic time masters, and then we look if there are any outliers. If there are any outliers in the subset, we just kick him out of the group and say, like, we don't trust you anymore, and then we use the rest to define our epsilon. Now, some might ask, like, okay, what if in one case, like in a zone, or even, in a zone, like all time masters fail? All my GPS and all my atomic clocks fail. What do we do? Is Spanner coming to a grinding halt? The Spanner is not coming to a grinding halt. We can go to a different zone and get the timestamp, the TrueTime interval from a different zone. But the epsilon will be larger because we have to calculate in all the round trip times for this call. So the database will actually slow down, but it will not come to a halt. Now, let's have a look at a query, like at the life of a query in Cloud Spanner. So in this case here, I have a consistent read where I want to select all the events, or I could say like all the talks, where the event name is like Devoxx 2017. Now, let's assume my client request comes in through a follower of my Paxos group. Now, the follower will basically ask the leader, because this is a strong, consistent read, will ask them, like with a timestamp here, is I have this timestamp of the data. Is this still the latest data for what was requested for me? Now, the leader might talk back and say, like, yeah, that's the latest data. And the follower can just serve the data. So the only data that moved between the follower and the leader is basically the timestamp. It's not actually the data, which increases scalability again. Now, there's another case where you ask the follower and the leader talks back and says, like, no, you don't have the most recent data. But the response will come with a timestamp and say, like, hey, like once you see this timestamp on your data, you have the latest data and you can respond to your client request. And that's what the follower does. It just waits out that time and then sends the response to the client. Now, there's a feature in Cloud Spanner which is pretty powerful, especially in the global replicated case. And we call that consistent stale reads, or time-bounded stale reads. Now, they are still strong consistent. With the timestamp basically that we use, like with TrueTime, we have always a consistent state, and we can basically travel back in time with, like, in a multi-version database system kind of manner. So what you define basically is say, like, okay, how much staleness do you allow? Or you can give actually a timestamp within an hour and say, like, here, I want to have the view of the data at that timestamp. Now, in my example here, I send a request and say, like, hey, I accept data that's up to 15 seconds old. Now, this is in most cases the case that the follower already has the data. So you should, like, the rule of thumb is to use about 10 seconds staleness if you want to have like a very high probability that the data is already at your followers. And then you basically ask like, hey, am I up to date? And if this is qualified, then the follower can just respond with the data without even consulting the leader. Now, what you've seen in all these scenarios for the reads, there were no locks. We don't lock for read-only transactions. Now, in the read-write transactions, of course, we have to acquire locks. So the requests, the client requests, get directly routed to the leader. And the leader acquires the locks, responds basically with the query results. So in this case, I might have done a select from something that I want to update. Then the client does some changes, some updates, modification on the data, sends this modified data to the leader. The leader basically sends out the writes to the followers. As soon as the majority of these followers comes back and says, yes, I have committed this data, then we can release the logs and we can send back a transaction success. If it's not successful, we send back a transaction on board and the client can retry the transaction. Now, this is a scenario for one split. Now, if you have multiple splits that are involved in a read-write transaction, then you use a two-phase commit protocol to synchronize between and communicate basically between the different splits. All right. With this, I'm going to switch gears a little bit and show how to get started with Cloud Spanner. So your first start is cloud.google.com/spanner. It is a fully managed service, so unfortunately there is no open source version that you can use right now. You have to use our fully managed version. Now, you find a multitude of information on this, like comparison to traditional databases or NoSQL databases. I don't want to go into detail in that. You can find me afterwards if you're interested to have a discussion about that. Now, I want to point out one thing. Cloud Spanner is not a one-to-one like lift and shift from a traditional relational database. You have to put some work in because it is a distributed system. Now, there is an article, especially if you're coming from a sharded MySQL system and you want to know how somebody else has done the migration, you can check out the Quizlet blog, which is a very technical, detailed blog about all the decisions that they made when they migrated from a sharded MySQL. There's also always the questions like, okay, how does Cloud Spanner relate to the cap theorem? Does it defeat it, yes or no? And I'm gonna make a note at the end if I have enough time for that. All right, so everything starts in the Google Cloud Platform console. The way to get to Spanner is like either you can use the hamburger symbol here on the left and look for Spanner under databases, which you find here. You can click here in the search box, or if you're a Vim user, you just use Vim search shortcut / and then type in Spanner. Now I go to my Spanner. I can go create instance. In this case, I do Spanner Devoxx. And then I select a region, and currently we support 4 regions. I choose Europe West. I say I want to have 3 nodes. I'm going to click create, and within seconds, I have my instance at my disposal. Now I can create a database in the schema here in the console, but I'm going to switch to our Java client to show how you can do that with the Java client. Now, first things, just to check, do a pulse check. Who is using Maven here in the room? Okay, Gradle. A little underrepresented. Okay, so I'm using Maven here as well. It's a love-hate relationship, I think that everybody knows. But to get started with Cloud Spanner, you basically need 3 packages. First, of course, the Google Cloud Spanner package, currently in 0.26 beta. And then you need the Guava and the Google Auth library, Auth2 library to get started. Now, I've created already a class here, fresh class. As you can see there is on the left side a backup Spanner playground. So if I fail to code correctly, I'm gonna cheat. All right, first thing that we need is we need to authenticate against the database. And it's pretty easy and cool actually to do this. Why is it red? doesn't want me. Oh, of course, we need a class function first. All right, let's start with this. All right, so first of all, I need an authentication process context. So it's very easy if you have installed gcloud SDK or you're running your code on a GCE instance, you have a default authentication context. Now you can get that very easy with Google Cloud. Just get application default, and then you basically authenticate it against the project that you currently have active with gcloud. If you want to authenticate to a different project with a service account, of course, this is possible as well. I'm gonna skip that to do this right now here. Now the next thing that I want to do is I want to have my Cloud Spanner playground. So let's do Spanner playground and Cloud Spanner playground. All right, cool. Next thing I want to do is I want to get actually some options. So let's create the client stub. All right, cool. So you need to get some options. We can get some information from the authentication context. So the first of all, I use the Spanner options builder. Get a service from there, use an instance ID. We just created Spanner Devoxx, and I use a database, in my case here, a demo database. Now, the first thing that I want to do is actually, I want to create a database, and I'm gonna just create a function to do this. So let me get out of here. And let's say, Spanner Frank, and then I call this create DB. All right, so I have my create DB Spanner instance function. I have my background. I do create DB, and I give it all the information it needs. So it needs a project, which is in my options. Project ID. I need an instance, and I need my database. All right, cool. So the first thing that I need here is actually I need to create an admin client. So if you do any kind of like administrative work on Spanner instance, like creating a database or changing a schema, you have to get an admin client. Now, where do I have that? Create DB. So I get my admin client here with get database admin client, and then I create a database where I just provide the instance ID, a database ID, and then a list of my DDL statements. So in this example here, I create an account table with 3 columns and an address table. So I want to point out a couple of things like bad practices basically to you. So first of all, you don't want to use any like monotonically increasing or decreasing IDs in your tables. So if you come from a world from MySQL and you're a heavy user of auto increment, bad for Spanner. The reason for this is, I can show this really quick, is this. So what happens if you use something that is monotonically increasing? I mentioned that we split the table lexicographically on the primary ID, on the primary key. Now, if you use something that is monotonically increasing or decreasing, like an ID that you generate like a sequence or timestamps, for instance, then all your changes, all your inserts and updates where you change the primary key to the latest timestamp, or use the latest timestamp as a primary key, all that ends up in one split. And the split is controlled by one computer source. There is no multiple. We do some splitting over time with statistics, but there's only so much that you can do if you always append to your table. So basically you end up in one split, and by that you restrict your horizontal scalability. Now there is an overcome that you can do. There are multiple things that you can do. One of them is you can use a shard ID. So you basically can use a shard ID here, for instance, and with that you can basically distribute between your splits. Another option that I use in my example here is I use a UID that I generate, and for now I actually gonna run this and create my database. Now next thing that I want to do is I want to insert some sample data. So I just gonna copy this because I'm lazy. I'm gonna put in here and to insert data. And then we create, did that work actually? Let's see if it worked. We have our instance here. We have a demo database. All right, cool. One thing to mention also is that in Spanner, you have like schema updates are actually online in a transaction. So you can, while your data is working, you can actually create a schema or involve your schema and make changes to it. And it's all handled within a transaction. So you don't have to bring down your system or anything like that. Now in this case, I want to insert some data. So Spanner insert accounts. Now this is, of course, only mutation, so I need something else first. So first I need a database client. All right, so database client or DB client. All right, new, nope, that was not what I wanted. All right. This is what I want. So we use database ID. And now here I want to have the project, the instance, and the database ID. All right, cool. Now I need my DB client and I want to do a write. I want to write some mutations. Now, what is a mutation? So basically in Spanner, in the Java client, mutation is basically what you do in terms of like changing any kind of data, be it single columns in your table or like adding rows or things like that. Now, what is special about mutations is that they are counted in a very special way. So if you do any changes in a table or in a table, so for instance, inserting data in a table and you have 5 columns in this table, one insert row in this table is 5 mutations. Now, if you have an insert defined on this table, you actually have, like, let's say you index 2 columns of your table, then you have another 2 mutations on top of this. Now, this is important because for Cloud Spanner, if you get at any point in time the error message that you have exceeded the transaction mutations limit, which is 20,000 mutations per transaction, then you know, okay, it's not like rows, it is actually the cells that you change in a table and in your indexes. So be aware if you use this. Now, in my DB client, I want to have a write. And then I do my mutations, and I get a timestamp back, but I skip that here. All right, so we're gonna create, insert some data. Now, next thing that I want to do is really quick, and since I have only 2 minutes left, I'm gonna cheat a little bit to be a bit quicker. So I want to do 2 more things. I want to have a read-only transaction, and I want to do a read-write transaction. And there are some special things with these 2 things. Now, my read-only function is here. And I copy this over and just explain the specialties around this. So if you do a read-only transaction, you basically get a single-use read-only transaction context. And then in this context, you can execute a query or can use our read APIs to query data. You can, as like common practice, you can use query parameters. So in this case, I use like a query parameter for my country code. And then you just run this really quick. Let me see. You run this and get some data back from our database if it worked. All right, so that's basically read-only transaction. Now there is something that you can actually do in this read-only transaction to get like this time-boundness, like this stale consistent read. So when you get the transaction context, you can add a time-bound spend and then say like 15 seconds here. And if I do that and execute that, I get the same data because this data is already older than 15 seconds. But this can be responded much faster, especially if you were in a global environment. Now, last but not least, I want to show really quick the read-write, and I'm not going to run it, but I'm going to show it to you because there's one specialty here. In a read-write transaction, you basically provide a transaction callable, and you write basically the run function of your transaction in a function. Why are you doing this, or did we decide to do this currently in our client library? Is that this way we can actually rerun your transaction in the client without you having to do the retry logic for transactions. All right, one note to Cloud Spanner and the cap theorem. Now, we get often asked, does it defeat it? And what I want to mention for that is cap theorem. Eric Brewer came up with this many years ago. That's the guy on the left, no, on the right, in this picture. And it basically says in a distributed systems, you have to pick 2 of 3 qualities of your system. 1, C for consistency, so that you always see the same data from any point where you ask your data. Then A, availability, that your data is always available, and P is for partition tolerance. So even in the like in the case of a split brain where you have like data separated from each other, it still works. So now if anybody comes to you and claims their distributed database system is a CA system, get really suspicious. There's only one CA system, or like one group of CA systems that are out there, and that's a single host database. So traditional database systems that are living on one single host, they are CA. But if anybody claims to have a CA distributed system, don't believe them. Now you have a couple of AP systems, which are basically in the phase of being partitioned or having a split brain. They still respond with data, but the data will be not consistent. And then there's a group of database systems that are CP, which basically they default to consistency in case of becoming partitioned. So if you have like majority voting and one partition of the majority voting still can get a majority in their voting, then this part of the database will still work, but the other part, which doesn't have majority anymore, will not serve any data anymore because cannot be sure that it has the latest data. And just to close out, Spanner is a CP system. In the case of that there is a split brain, you will have an unavailable system. But I wanted to say one thing for that is, like, if you look at the infrastructure and the architecture, which is underlying Spanner, it's set up in a way that this case is really unlikely. And we back that by an SLA of 4 nines, which is 4 minutes and 38 seconds for our regional instances, and 5 nines, which is 26 seconds for our global instances in availability. So we didn't have yet a split brain in all the 10, 12 years that we are running Spanner. With this, thank you very much for your attention and staying the 2 minutes more that I overrun. If you want to give me some feedback, I would be really appreciate that. And otherwise, I wish you a really nice evening. Thank you very much.